Hello, welcome everybody, and thank you for joining our Cards Digital Thursday webinar. The topic today will be simulation-driven design with Star CCM Flow. First, let me shortly introduce myself. My name is Vasco Keizer, and I'm active since about 4 years at Cards PLM Solutions. I have a technical background in automotive engineering, and my expertise within Cards is the SimCenter 3D portfolio. Furthermore, I'm responsible for the sales part of the rest of the PLM portfolio in the west and the middle of the Netherlands. Joining me today is Florian Vesting from the company Volupe. He is a CFD expert and he will be taking on the technical part of today's presentation. Florian, if you could shortly introduce yourself as well.
Thank you, Vasco. Yes, my name is Florian Vesting. I am since about 1.5 years within the technical support team here at Volupe in Sweden. We are Siemens partner and Platinum Smart Expert for the Siemens SimCenter portfolio. My technical expertise is mainly Star CCM Plus, Heat and AimSim. But I have more than 10 years experience in simulation-driven design and optimization with CFD.
Okay, thanks Florian. So for the agenda today, we started off with a short introduction. Next I would like to briefly discuss with you why simulation-driven design is important and what it actually entails. Then I will give the microphone back to Florian, who will talk about the data exchange between CAD and CFD, show you a simple workflow of setting up a CFD analysis within NX CAD, and finally move over to an optimization of the geometry. Let's first consider a typical product development process from incubation, where the product development effort is focused, through growth, maturity, decline, and finally end of life. Taking a typical product life cycle, the product is launched to market at the end of the incubation phase. It reaches a break-even point where the investment in development has been recouped through sales. Then eventually sales start to decline and the product is finally retired. Now to optimize this process, our goals are to minimize the area under the break-even point line and maximize the area above it. Exploring that further, if we can reduce the time taken and cost incurred during product development, we can enter the market sooner, potentially capturing increased market share, and similarly, if we can extend the life of the product, we can also positively affect the lifetime value. Now, one of the possibilities to achieve this is simulation-driven design. And when we're talking about simulation-driven design, we're talking about utilizing simulation in a different way than we used to do in the past. Consider how the use of simulation has advanced over the decades. Prior to the 1960s, the only option was to build a physical prototype of a design and physically test it to see if it would meet the performance requirements. Then starting in the 1960s, the first simulation codes started to be developed to support the space race. But these codes were still quite limited in their capabilities, so physical testing was still a major component of the development process through the 1980s. But as computing power was becoming increasingly cheaper, simulation codes were becoming more powerful and were beginning to cover more physical domains. Simulation began to replace physical testing as a means for validating if a design could meet performance requirements. However, it was still a complex tool requiring a lot of expertise. But today the tools, processes and expertise exist to make simulation-driven design a reality. And you can use simulation to discover new design concepts, as well as use simulation as an integral part of the detailed design process to get to the right design more quickly. So when we are talking about simulation-driven design, we are talking about using simulation throughout the development process. We use it to generate our first concept design, keep our simulations parallel with each design iteration, validating that we are making the right choices, and finally, of course, still validate that our product performance meets our requirements. Today, we will be looking in more detail at how you can keep your simulation in parallel with your design by having a tight link between CAD and simulation. Florian, the floor is yours.
Thanks again, Vasco. Then let's talk about data exchange. This is always a topic when it comes to CFD simulations and to get your cut geometry ready for meshing and for simulation. Luckily, SimCenter Star CCM Plus provides seamless exchange of CAD geometry through the CAD clients. So these clients are available for most of the established CAD programs and most certainly for NX. In this case, CAD geometry is fed directly to SimCenter Star CCM Plus without any intermediate file format transformation, something like that. So there's no quality loss to get the geometry into Star. And it's straightforward to get access to the Star solvers from your NX environment. And on the other way around, Star has access to all the design parameters to update the geometry in your NX environment. So this is very important when it comes to automated design exploration. You have always the most accurate and most updated geometry in your system. This bidirectional connection is actually live. So if I play this video, you can see that I have here my NX file and I change a parameter. So the geometry was changed, and then I can go and transfer my geometry to Star. And here in Star you can see that I have the same parameters, and this parameter already has changed live. And when I then update my geometry operations, then I have again the same geometry in both my NX and my star simulation. And this works not only through the network on different computers, it works also between different operating systems. So if you have your NX on a Windows machine, you can access that remotely from your probably Linux machine where you run SimCenter Star CCM Plus, and the other way around, if you run and set up your simulation on your NX, you can send out the simulation to be solved on your workstation, which is on another location. So this is typically what we get when you look at a CAD part. It's a very detailed geometry, possibly ready for production and in your PLM system with all the components. But this is actually more what we need for our CFD analysis, which would be the inner volume of this valve, which can then be discretized and specified with boundary conditions to solve the flow inside and to solve the governing equations there. In NX you can do that by using the functionality extract geometry. Here we have a pipe system, and we don't have anything inside the pipe system, but this is actually the region that we are interested in and that we need for our CFD simulations. So we select the body, for the extraction, and then we need to delete all the faces which are not necessary and which come with the extract geometry. So I select the inner part, and then I invert my selection, and then I have the inner volume, which I then can use to discretize. So once you have your CAD client installed, it provides you the integration provides you with a workflow for your seamless data exchange. You get two new features. That one is the CAD client tree, and the other one is the CAD client NX ribbon. In the tree, this is a straightforward workflow to set up your simulation from bottom to top. You can define your physics continuum, the flow of your physics. Is it a solid? Is it a gas? Is it a fluid? And all the properties. Next, you specify which region you are going to discretize and which boundary this region will have. So we can have several regions, like in this case. Here we have a fluid domain that's stationary. Inside we have a fluid domain which is rotating with this propeller here. Then we have a region for the steel pipe, and on top of that we have a region for the insulation. All of these have different boundary conditions, and all of these have different discretizations possibly. And last point is to mesh that, because the mesh is of course related to your boundaries, and that affects the meshing. And here you can specify your prism layers, for instance, and control where you want to have refinement depending on the curvature, for instance, where you need to have a refinement, how much how much the cell size is growing in the direction from one boundary, or how much you exactly relate the mesh to your actual geometry. Next is the CAD client NX ribbon that provides you with all the possible inputs needed for to set up the simulation and to control the solver. Here you can specify your solution controls, and you can specify your running setup if you run in parallel, if you run on a remote host. Here you can specify if you want to run and build your mesh and run the simulation directly from NX. And then you have the export options, where you just can export the CAD geometry, you can export the mesh, and you can export the complete simulation setup. So let's have a look how this looks, how this can be done in real life. So here's the demonstration. And here comes my Star CCM Plus tree, and now I'm going to set up the continuum. First thing, we use a liquid here. I'm not interested in the temperature right now, but I could specify that as well. And but I use the default values in this case. For the density, it's fresh water. And then I add I have already the region selected, because I just have one region. It's only one part. It's not a assembly. And then I can provide my region with boundary conditions. So I add a new boundary for the inlet. In this case, it's a mass flow. This is a real investigation of a real pipe system. So I didn't come up with these values. So now we have some flow going in, and then we need to have some flow going out, and therefore we select a pressure outlet and select the phase here for one outlet. I need to have several outlets, because I want, in a later stage, I want to compare the mass flow at these outlets. So this is now a bit repetitive, but this is now the last one, pressure outlet, 0 reference pressure. And then I go to set up the mesh controls. Because for the inlet and outlet, the mesh solver will not create any prism layers at the outlet and inlet boundary conditions. But otherwise I go pretty much with the standard. I create a polyhedral mesh type. I change the maximum prism layer here to 22%. It's all relative to the geometry size. It's a good starting point. If you want to change your mesh, then you can start from that and change it. Then I switch to the Star CCM Plus ribbon and can start with the surface mesh. This is the starting point for the volume mesh then later. And here you can see that I have already created the volume mesh with the 3 prism layers that are specified. So next is to provide information for the solution. Go to the solution controls, and there you have a slider. There you can specify it's a preliminary design or is it a design validation. Then it of course needs to be more accurate. And you see here when I change the slider that it switches the under relaxation and the total number of iterations. Then I can also specify that I want to run a parallel on the local machine with 4 cores. But here you can also specify the license option and if you're running on a remote machine. But of course these changes will only apply if you restart the license, the CAD client. So I built and run it. Then you can see the how it actually converges, and then it opens. Once it's done, it opens Star CCM Plus for post-processing. It provides you with an initial post-processing scene, and then you can do the post-processing in Star to, for instance, create a new Scala scene. And there we provide some streamlines which seeds from our inlet. Here they are. If you do then some more post-processing, we can add the velocity, we can add a field function that shows the color. And then we can add the outlets and fill them with some coloring of the pressure mass flow rate. And finally, to get a better understanding of what we are actually looking at, we can add the actual geometry, surface, finally, if we have done that with the baseline design, we can start our optimization and get really some value out of our simulation and our setup here. The pipe system that I showed you, mass flow of the 3 outlets should balance, so there should no difference between the 3 outlets, and you see that they have different diameters and they are differently located. So this is not an easy task to do by hand. At the same time, I want to minimize the pressure drop of the whole pipe system here. So what I do is I change a fixed plate, how much it is actually closing up or opening up this area of the outlet, and these are my 3 parameters that I changed during the optimization. So how you do that? Once you have done your first setup of the baseline, you can just create a new project, design manager project, and there you see your simulation with all your report scenes, plots, and parameters. Then you can create a new design study. In this case, we want to do an optimization. And this is now very important because this is the only time that you have to interact with the optimization algorithm. So you just specify how many numbers, how many variants you have time for and you want to create. Then you select the input parameters. Again, these are the parameters from the NX setup. I'm doing a fast forward to actually set up the parameters, the maximum value and the step size, and then you add some responses. In this case, it's the total pressure drop and the difference between the 3 outlets. And you can check all the time if your simulation is already your design study is already ready to run. But now in this case, we actually have to provide if one of the responses is actually an objective. In this case, we both, and they can be normalized. I choose to normalize them as the baseline. Then I select set up the run conditions if it's run locally or with a remote machine, and then press start, and you can observe how the simulation actually goes through. And what happens in the background is that it starts every time it creates a new variant, it starts NX in batch and changes the geometry, and then run each variant in Star. Once you've done with all your simulations, you can create a Pareto plot, for instance, see what are the the best designs for the 2 different objectives. You can add the other created variants as well, and if you put them in one plot, you can go through your design table and see which of these designs is actually which design in your design table. And then you can on top of that, you can create a parallel plot where you have the responses on this axis, one response, pressure drop on the other one, and the 3 parameters. And you can mark your best designs and see where they actually have their parameters, which parameters are actually leading to these good results. So with this last slide, looking at the actual optimization, you can see how the algorithm then gets less and less mass flow difference between the 3 outlets, and how the flow actually develops for this. And here you can see how they opens and close, how the algorithm open and close the different outlets, and then in the end it converges to very little difference between the 3 outlets. And with this convergence, I actually converge to the end of the presentation. Thank you very much.